Good morning, everybody. It should be Monday, April 20th, or maybe some other time after that. It's me, Mr. Deserich, again, and I do have my new headset, which is pretty exciting for me. So hopefully my sound quality will be much better. And today we're going to talk about using the equations of lines of best fit. Yesterday, last week, last Thursday, we found out how to find the equation of a line of best fit. Now we're going to talk about what we're going to be able to use it for. Okay, so here are the materials I would like you to have today. I want you to have Microsoft Teams open. YouTube should be open and you're already there because you're hearing my voice. Go to joinpd.com and put in the code that your teacher has given you somehow. And let's see, you'll want to go to clever.com/in/DSST so you can take a mastery check on Edge Elastic at the end. This video will step you through every single part of the lesson, so your teacher's there to answer questions if you have them, but just please know that you can use the video at any time to answer your questions. All right, also I'd like you to have some pencil and paper for some scratch work today, just in case the space you have in Pear Deck is not going to be enough. All right, so with that, let's go ahead and get into the do now. There are two do now questions today. The first one asks you to find the slope of the line of best fit pictured here, and that's the lesson we learned yesterday, and you've got a pro tip right over here to help you out with that. The second question on the do now is to find the whole equation of the line of best fit, not just the slope on this one. And there's a lot more space here on this slide for you to be able to do that. So please go ahead and pause the video and do these two do now questions. Remember, your teachers are going to be checking these do now questions and both giving you feedback during the lesson as well as grading them. So please make sure you put your best into this so that you can get the full learning out. So pause the video for a second. Well, it might take you longer than a second. Go ahead and pause the video and go from there, please. All right, hopefully you got that taken care of. Here we go. It wants us to find the slope of the line of best fit pictured here. We want to make sure we pick 2 points that are on the line. And so I'm going to pick, it looks to me like a good point right here is on the line at 2,800. I'd say that's one of our points. And you may have picked another one, but I mean, I'm going to look at another great point, like a great point of intersection. I'm going to go up to here, it looks like. I'm going to choose 1200. Okay, so now we just need to do y minus y over x minus x. We'll do 1200 minus 800 over 8 minus 2. So that's 400 over 6. A couple different ways we could write that. Let's go ahead and reduce. I know that these are both even numbers, so I'm going to divide both of them by 2. That will reduce the fraction. That gives me 200 thirds. And if that wasn't one of the options, then let's make sure we look at our calculator. So pull out a calculator if you don't have one. You can just open one on your screen. And I'm just going to do 200 divided by 3. We'll go 66.7 because it didn't tell us what to round to. So we'll just go 66.7. I know it's 0.6 repeating, but either of these answers will be acceptable. And if you saw them on a multiple choice test, you won't see both of them on a multiple choice test. So one would be, you'll only see one of the two. Okay. Now, question number 2, it asked us to find the actual equation instead of just the slope this time. And so we do want to use the points with the arrows. So we have these 2 points already chosen for us. So really that's all we need from the graph. From here, all we need to do is find the slope and find the y-intercept. I have enough room here, but I'll go ahead, since I encouraged you guys to, I'm going to go ahead and bring 25, 90, and 765 down to the next slide. Hopefully you did your work there, and we'll see how we did. We can go 90 minus 65 over 25 minus 7. That looks to me like it should be 25 over 18. And so you can go ahead and leave it like that if you'd like. That's a fraction that can't be reduced, but as we go into this format of y equals mx plus b, I think it's going to be better to just use a decimal this time. So I'm going to estimate it as a decimal, get my calculator out, and do 25 divided by 18. So I'm going to call it 1.38. I'm going to call it 1. Yeah, I'll call it 1.38. No, 1.39. Because the next number after that 8 is another 8, which would round us up to 9. So I'm going to go with y equals 1.39 times x plus b. and you can choose either of the 2 points we were given. I'll go ahead and choose 765, where 7 is the x and 65 is the y. So 65 equals 1.39 times 7 plus b. I'll use my calculator for 7 times 1.39. Sorry about the flashing there. So I'm just going to clear this. 1.39 times 7, 9.73. So now we've got 65 equals, I just forgot that one. I don't know why it's doing that, 9.73 plus b. So I'll bring that up over here. We've got 65 equals 9.73 plus b. We'll take away that 65 from both sides. And we are, nope, that doesn't make sense, sorry. We don't want to do that. We want to take away the 9.73 from both sides. That'll leave b alone. And so this equals b on the right side, and on the left side, we'll go ahead and figure out what 65 minus 9.73 is. So 55.27 is our y-intercept. So hopefully you got y equals 9.73x plus 55.27. If you struggled on that one, that might be something you want to see your teacher for in office hours. This is a skill you definitely need to be able to take with you to 10th grade as you get ready to go on to the next year, 10th grade or 11th grade, depending on where you're at right now. Okay, and I have made one more mistake. Man, I'm a little rusty here. The slope was not 9.73. That was just a number we had used. The slope was 1.39. So hopefully you've watched this whole video and found out that I make several mistakes. So I'm just getting back into the swing of things here. It's Monday for me as well. So let's go ahead and make sure I've got everything right. Got the slope right, plugged it in, multiplied by the 7, subtracted it from both sides. I feel better now about where we are. Okay, so I make mistakes too, and that's totally okay. We'll recover from them. Here we go. I'm going to sell a couple celebrations here. These are the people that sent us the Marvel superheroes of the day from our very first video on Thursday, April 9th. Clara Madrano from our own Montview High School and Damien Lucero from College View were the ones that told us that Iron Man was the superhero mentioned in the video. So congratulations to them. Give them a round of applause, or if you know them, send them a message. And then I thought we'd celebrate a few of the great drawings we had on Thursday, April 9th as well. We had Lexi from College View with a monkey here, and Jocelyn with a nice lion, also from College View. Luis from College View got a sloth, and Malaya from College View has this nice SpongeBob. Looks like SpongeBob's maybe sunbathing. We got Jesus Salinas from Cole with a nice dog with maybe I don't know if he's got like a little bandana on or something. Mylea from from Montview, she's got a nice dolphin there. And Mia, in case you weren't aware, this is a chicken, she tells us, and it truly is a chicken. And Jimmy is a big fan of Pear Deck because he likes to draw this frog, sometimes instead of doing his math. But he did his math today too, and I appreciate that. So Mia and Jimmy are both from Montview as well. All right, here we go with today's lesson. So you've seen the word scatterplot and line of best fit in both of our last two lessons. You're getting comfortable dealing with scatterplots now, hopefully, and you're feeling better about drawing lines of best fit and finding their equation. Today we're going to talk about why do we need to find the equation of a line of best fit? What's it going to do for us? And there's several different things that it can help us do. We're going to start here with a little exercise, not actual exercise, but an investigation. Have you guys been getting enough exercise at home? It's kind of sometimes tough and you're stuck inside, and so hopefully you're getting enough exercise. We're gonna about how many hours of exercise do you get per week? I myself, if you want to think like actual exercise, like where I'm working hard enough to get my heart moving, for me I'd say is probably about 4 hours a week. I'm gonna change the color of my pen. I like purple better. I do about 4 hours a week. I don't know about you, but that's what I do. So why don't you write that down there? How many hours of exercise do you get every week? All right, now we're going to measure your heart rate. So we're going to do that together here, and I want you to find your pulse on either your wrist or your neck. I like to find mine on my wrist. So I am going to get mine going there. I can feel it. Try to find yours. I'm going to set a little timer for I just want to set a timer for 10 seconds, okay? So when I say go, I want you to count as many beats as you can during this 10-second time period, all right? Hopefully you've got your pulse found. Ready, set, count. Okay, so stop your count and let's go ahead and write here how many you've got. So I've got about 11 in that amount of time in 6 seconds or in 10 seconds. Okay, and so what did you get in 10 seconds? What we actually want to do is we're going to multiply this by 6 because we want to have how many beats there were in 1 minute. And obviously there are 60 seconds in a minute, so we need to multiply whatever we got in the 10 seconds by 6 to equal the 60 seconds that there are in a minute. So my 11 times the 6 will be 66 beats per minute. And that's a pretty common term in the medical and fitness fields is beat per minute. So 66 beats per minute. All right, let's see how that compares. So here are the results from a different group of people, including the line of best fit and the equation of the line of best fit. You may have been in a different place, but again, I exercise, I said about, what did I say? I'm sorry. I said about 4 hours per week, and my heart rate was at 66. So at 4, I was at about 66. I was pretty close. Where do you fit in on this? But more importantly, what do you notice about the relationship that you see right here on this scatter plot? Go ahead and take just 10 seconds and type in the box. What do you notice about this relationship? Hopefully you notice that there is a negative correlation or association. That is one thing that I noticed here, is that we see a negative correlation between this, that as the number of hours of exercise increases every week, our resting heart rate will decrease. So the more you exercise, the less your heart has to beat to keep your blood moving. And so that's one of the reasons that exercise is good for you. It makes your heart stronger and it can send the blood through your body with a lot fewer beats. So it's a good strong heart and doesn't have to work quite as hard when you exercise more. Now, the whole purpose of today is to be able to use lines of best fit to answer questions. And here's a few of the kind of questions that you'll see from a line of best fit with this specific equation and the line of best this specific line of best fit and its equation. So it asks us to use the equation of the line of best fit to predict the resting heart rate of someone who exercises 12 hours per week. Great. Okay, so this is one big use of the equation of a line of best fit is going to help us make some predictions. Now, yesterday or last Thursday, we might have tried to extend the line, but it's going to be inaccurate. And so now that we have the equation, it's going to be a lot easier. So if someone exercises 12 hours per week, 12 hours of exercise appears to be the X value. So we can use our equation and we can just take and put 12 in where the X was and do the math here. Sorry, I was getting a little ahead of myself. So this gives us negative 48 plus 79, and so y equals 31. So the predicted heart rate, the predicted y heart rate of somebody that exercises 12 hours per week would be 31 beats per minute, which is pretty low. I don't know if this actually holds true, but according to this prediction, this line of best fit, that would happen. So that's one thing you can do with a line of best fit is make predictions. Another thing that they might ask us about lines of best fit is really just what does the slope represent? And this goes all the way back to first trimester, where anytime we were dealing with the slope, we always talked about how it represented a rate of change. And so in this situation, the slope of -4 would represent the rate of change of the decrease, because it is negative. I don't like how it's going all the way over there, so let me get it here. The decrease in heart rate per hour of exercise. So showing that your heart rate will go down every hour you exercise. Now, one thing we do need to add in this situation is it's not an actual. This line of best fit is always a prediction. And so we want to make sure that in our answer we would have something like the predicted rate of change of the decrease in heart rate per hour of exercise. Okay, so those are some keywords in this one, is that we have the word predicted in there. That's the most keyword we would have in this. And the other parts are things that we did back in first trimester where we talk about how slope represents a rate of change. And this one in particular is a decrease because it's negative. And then will always be the rate of change of the y variable per the x variable. The y variable in this situation was the heart rate, and the x variable was the hours of exercise. Okay, we'll talk a little bit more about that in the next in a minute here. But that's another thing we can do with the equation of a line of best fit. They might ask us just what the y-intercept represented. The y-intercept always represents the initial or original value of y. And in this situation, y is representing, let's look at our graph, y represents the heart rate, the resting heart rate. And so we're going to say it represents the initial value of the heart rate. You could put resting heart rate if you'd like, because it does have that in the title, but in the end, that is the initial or the original value of the resting heart rate. But again, when we're dealing with a line of best fit, it is just a prediction. So we need to add at the beginning the predicted initial value of the resting heart rate. So basically a predicted original value, it means your original value, if you exercised 0 hours per week, your resting heart rate would be predicted to be 80 beats per minute. Okay. And then one other thing they might ask us to do about when we have the equation of a line of best fit is they might ask us, like, how far is the prediction from the actual? So it says one person in this study who exercised for 6 hours had a heart rate of 58 beats per minute. How far away was that from the prediction of the line of best fit? So the arrow is actually pointing to who they're talking about. With 6 hours of exercise, this person had a coordinate of like 6 hours of exercise and 58 beats per minute. Now the line of best fit actually says we should have been at 55 when we are at 6. So that at 6, I don't like that, I'm a little too small there. At 6 hours, we should have the line of best fit predicted we would be at 55 beats per minute. So how much higher is 58 than 55? It is really 3 beats per minute higher than predicted. So that's one last thing that we'll talk about, is that the line of best fit, line of best fit and the equation of line of best fit can help us see how far above or below our prediction somebody's actual value was. All right, so moving on to take some notes here. Please make sure you join me in taking these notes. These are pretty easy to type into the Pear Deck slides, and so just do that along with me and you'll get full credit on this. So one thing we can do with a line of best fit, with the equation of a line of best fit, is that we can use them for interpolation, for predicting points in between the smallest value and the highest value, or extrapolation, finding the values of points outside the smallest and biggest x's. So if we are given the x value, all we have to do is plug into the equation to find the y value. That is one thing that they'll let us do, that an equation of a line of best fit will help us find. And then obviously the other way it goes around too, if they give us the y value, then we'll plug that in to find the x value. I know that this can be kind of tricky sometimes to get it to right where you want to. Just do your best and change the color. Sometimes that will also help. Okay, so if we have an equation of a line of best fit, we can use the x value to find the y value, or we can use the y value to find the x value. And we'll have an example of that right here. Miss Grimstad was bored and measured the amount of water that flowed from her hose over the course of 30 minutes, and then plotted the data below. She even drew a line of best fit and found its equation to be y equals 4/5 x. At this rate, approximately how many gallons of water do you predict will flow from the hose in 45 minutes? All right, so we're going to use our equation of line of best fits. They want us to make a prediction of how much will flow from the hose in 45 minutes. Where is minutes? Minutes is along the x-axis. Okay, so minutes is along the x-axis here, 45. So that's our x. is 45. So what we want to do is we want to use that to plug it into the equation. Y equals 4/5, and instead of the x, we're going to put 45 because that is the value of minutes that they gave us. It's pretty easy if you want to go 4/5 times 45 over 1, and that would give us, I should be able to do that in my head, 180 divided by 5, and check your calculator here. Nearly positive we've got 36. I'm going to double check that on my calculator real quick. Go ahead and do 180. Move myself. 180 divided by 5, 36. Okay, so then that means we would predict that 36 gallons would flow in the 45 minutes. Okay, so that's one example of how we can use this. Next, another slide of notes here. And this is just going back to the first part of the conversation where they talked about if in a line of best fit, the slope will represent, we know the slope represents the rate of change. We have talked about that quite a bit in this class. But if it's a line of best fit, the slope represents the predicted rate of change. So we really want to use that idea and that concept of the line of best fit being a prediction, not an actual value. And the y-intercept also represents the predicted initial amount. Again, we knew the y-intercept always represents the initial amount. In this situation, though, when it's a line of best fit, the y-intercept represents the predicted initial amount. Okay, so when they ask us, same situation up here, but the question is now asking us, what does 4/5 represent in this situation? 4/5 is right in front of the x, so it does represent the slope, but we want to be a little bit more specific here, and we want to say 4/5 is the predicted, make sure that word is in there, predicted rate of change of, and then you put the y variable per the x variable. So of the y variable is gallons per minute. You can also do, you might want to add the idea of an increase. 4/5 is the predicted rate of change of the increase in gallons per minute. Okay, a couple of the different ways you could write this. I'll put them over here. One is, like, I know a lot of you guys like to write this, 4/5 gallons, 4/5 of a gallon flow every minute. But again, you have to add the predicted idea. 4/5 of a gallons are predicted to flow every minute. Some of you guys might want to also put 4 gallons are predicted to flow every 5 minutes. Okay, again, this is an older concept that we've used before, but it's now bringing in the word predicted because when we're talking about lines of best fit, those are predictions, not actuals. And then lastly here, the line of best fit, remember, is just a prediction. Sometimes the actual does not match the prediction. So if you want to find the difference, if somebody's asking us the difference between the actual value and the prediction, all we need to do is subtract the y-coordinate of the point, so whatever point they're talking about, and it'll make more sense in just a second, the y-coordinate of the point from the y-coordinate of the line of best fit. So let's look at this next example here, and they tell us, okay, same example from Miss Grimstad. She was bored and measured the amount of water that flowed from the hose over 30 minutes. About how many fewer gallons of water flowed at 15 minutes than predicted? So we go to 15 minutes, and we actually look at the actual point here. The actual point is at about, I'd say, 9 gallons. The predicted, you see how the actual point is over here at where 9 gallons would be? That's the y value. The predicted value is the one that's on the line of best fit, which was 12. Okay, so all we need to figure out is how far 12 and 9 are apart, which is 3. And so we would probably write something like 3 fewer gallons flowed, and I'm running out of space here, 3 fewer gallons flowed than predicted. Okay, so we want something like that there. So we're just finding out how far away the actual point was from the line of best fit, which was the prediction. Great. Okay, hopefully you're feeling good about this so far. You can now use a line of best fit, the equation of a line of best fit, to interpolate and extrapolate. You can also explain what the slope and y-intercept of the equation of a line of best fit represents, and you should be able to use a line of best fit to find the difference between the actual and predicted values. So that will lead us here into our independent practice. There's no Khan Academy today. It's all going to be here in Pear Deck. So please go ahead and pause the video now and try all 1, 2, 3, 4 questions in the independent practice, and then unpause the video when you are done. Now you can do it a different way. You can do just one question, then unpause the video and see that, like, you pause the video, do one question, unpause to see if you're right, and then go on to the next one. Both of those are okay. I will read the problem situation to you here so that you can use the closed captioning if you need to, and then I'll encourage you to pause the video. All right, Zhang Lei creates and sells wreaths. The scatter plot below shows how the diameter of her wreaths relate to the weight of her wreaths. About how many pounds away from the prediction is the actual weight of a wreath that is 36 inches in diameter? So go ahead and pause the video, try this one, and unpause when you're done. Okay, so hopefully you've done that. So about how many pounds away from the prediction? Yeah. So let's check the prediction here. At 36 inches, the prediction was 10. Can you see that? At 36 inches, the line of best fit, which represents our prediction, was 10. The actual, though, was only 8. So really the prediction was, or the actual was 2 lower, 2 pounds. Let's go ahead and put 2 pounds lower. We can use 2 lbs lower than predicted. Okay, that's all we needed to have here. Let's check the next independent practice slide. Same situation, same problem situation. This one's asking, what does the slope of 0.4 represent in this situation? Try to answer your question right down here below, and then unpause the video when you feel like you have an appropriate answer. Go ahead and check your notes if you'd like. The notes are right up above, and you can use those to try to craft a great answer here. Okay, so hopefully one thing you've gotten out of today's lesson is the idea that you need to use the word predicted when you're talking about slopes and y-intercepts from lines of best fit. So 0.4 is the predicted rate of change for, let's see, which is the increase in, I'll just go pounds per inch. I would accept that answer. This is, it's an increase in pounds per inch. Some other appropriate and acceptable answers I would say is the weight is predicted to increase. Sorry, I know it's getting further away from the problem situation there. Let's get that back. The weight is predicted to increase 0.4 pounds per every inch the diameter increases. Okay, a little more nuanced answer there. I would accept either of these. Just we want to make sure we have the idea that it's a prediction, and it is an increase in pounds per inch. All right, third question here. We're going to use this to do some extrapolation. So the problem situation here says the equation of this line is 0.4x minus 4.4. Predict the weight of a wreath that has a diameter of 50 inches. Pause the video and try to find that, and then unpause the video when you have it. Okay, a diameter of 50 inches. What variable is that? Diameter is along the x-axis, so they've given us an x. So we just need to plug it in here. Y equals 0.4 times 50 minus 4.4. So y equals, we'll go ahead and do 0.4 times 50 on our calculator. Okay, which is 20. And so we have 20 minus 4.4, which I know to be 15.6. So 15.6 pounds would be the predicted weight of a wreath that is 50 inches in diameter. And does that follow? That seems to follow pretty well. 50 would be maybe somewhere out like right here. And that seems to follow pretty well with about 15 pounds on the weight. Okay, and last independent practice problem here. This time they want us to predict the diameter of a wreath that weighs 11 pounds. Okay, if it weighs, oh, sorry, go ahead and pause the video, please, and do this problem first before you unpause it and listen to me. Okay, hopefully you did that. Again, they're going to ask us to predict. We're going to use our equation of a line of best fit, the diameter of a wreath that weighs 11 pounds. So if it weighs 11 pounds, we notice that pounds is actually the y-axis here. So they've given us a y. So then our job is to go ahead and plug that in where the y was. The y is the first thing in the equation. So we're going to put the 11 there equals 0.4x minus 4.4. So now we'll go ahead and add the 4.4 to both sides so that we can get y by itself. Or sorry, so we can get x by itself. This is 15.4 equals 0.4x. Now, most of you know we need to divide both sides by 0.4. Let me check that one on my calculator. Should be somewhere. Well, let's just check it. 15.4 divided by 0.4. All right, so let's see. That seems right to me. We could have checked on this one a little bit. 11 is right here on the y-axis, and if we go over to our line of best fit, we are pretty much right at 38. I know that the prediction here, the calculator tells us, sorry, 38.5, and so that's a little bit more accurate, so we are going to go ahead and go with x equals 38.5 inches. All right. So hopefully you are now able to, so hopefully you can fully meet all these expectations now, being able to use the equation of a line of best fit to interpolate or extrapolate, make those predictions. You should also be able to explain what the slope and the y-intercept represent, just basically that they are predictions, and predictions of the rate of change and predictions of the initial amount. And you should also be able to use the line of best fit to find the difference between the actual value and the predicted value. So with that, you should go ahead and go on to the mastery check, which will be week 3, module 1, using lines of best fit. We are going to grade that mastery check, so do your absolute best. Use your notes if you need to. Ask your teacher questions if you have them, and have a great day.